libraries. So these slides come from a course we gave called the Fomics Autumn School in GPU-enabled libraries. It was an intense 2-day course, grueling 2-day course, Saturday and Sunday, where we just went from 8 till 5:30 nonstop with exercises. So that was a 2-day course, and I'm packing that all into the next hour and a half. Lucky you. So, but we have plenty of time because I've got a few extra minutes. Alfio talked about libsci, essentially. Well, libsci, as he pointed out, isn't the only library available. There are a lot of possibilities on GPUs. And I'll be talking about some or most of the following. One, I'll talk about the sort of numerical and semi-numerical problems which our users tend to come to us with. And then some of the GPU-enabled libraries which are available. And Alfio already mentioned these in some form, things like QBLAS or QXX, QBLAS, QFFT, so forth. Magma, he mentioned. I don't think he mentioned Thrust and Cusp, Vienna CL, Parolution, PETSI, he also mentioned, and Trilinos, I think he mentioned. There is a website for the course we ran. It was a very good course, I thought. The reviews were very good. There's a lot of material there. It's open to the public. So you too can just go to the course. And in fact, during this lecture, I'll see if we have time for one small exercise from that course. Okay. Yes? Okay. Shall I try another resolution? Yeah. Okay, so now you're at... And if there's enough interest in this course, we will hold it again, not this year, presumably. We think we have a pretty full schedule. But if you're interested in more extended look at these GPU-enabled libraries, let us know, and perhaps we'll schedule it for sometime next year. Okay, we got the thumbs up from Maria Grazia. Okay, the objectives. First, I just want to let you know that these third-party libraries are available, and it's not always necessary to recreate the wheel, right? Particularly if you're a scientific developer. It's not always necessary to go out and rewrite the QR decomposition, right? Because a lot of really qualified, good people have already done that, and your version will never perform as well as their version. I'm going to give some of my own opinions about which are the libraries to bet on long-term and which maybe you shouldn't bet on long-term. This is a slide from Nvidia, actually, from Peter Messmer, who some of you might know. And it's the library ecosystem for CPUs. And he split it up into a taxonomy for multi-node and single-node, right? So distributed memory, single node, shared memory, and then for sparse and dense problems. And things over here, IDL, Python, things for simple workflows. Then over here, there's something called the sparse BLAS. Then for multi-node, you've got things like PlayPack and ScalaPack. I assume you know what those are. And then, interestingly enough, over here on the sparse side, there's a huge number of libraries available. Things like SuperLU, MUMPS. These are direct solvers for large sparse systems of linear equations. PESTIX, Paradiso. These are really extremely good libraries, but they're only available on CPU, right? And so what you'll find after the end of my presentation is there's virtually nothing available here. It's very, very sparse. The sparse multi-node is very sparse in terms of GPU-enabled libraries. Okay, we will get to that. So these are the types of problems you might have, many of our users come to with for partial and, of course, also ordinary differential equations, dense linear algebra. I know several of you are doing dense linear algebra. Sparse systems of linear equations. This goes almost always hand in hand with partial differential equations. Preconditioning, that goes again with these two. That, well, I'll get into preconditioning pretty soon. Eigenvalue, singular value decompositions, partitioning large graphs, optimization problems, and then the list goes on. But a lot of our users come with these problems at the top of the list. So what's available? For single node GPUs, right? We're not talking about multi-node until the very end of the talk. So there's solid support for dense linear algebra. And Alfio mentioned that. I'll mention some more. Obviously, there's also Magma as well as libsci. There's some limited support, as you'll see later in the talk, for sparse linear systems, sparse preconditioners, or preconditioners of sparse systems. And there's a lot of development ongoing, but there's actually really nothing solid available, the exception possibly of eigenvalue solvers. And that's an unfortunate circumstance. We have this nice machine, but we don't have the library support we really would like yet. Okay, so let's start with NVIDIA's CUDA libraries. And Alfio already mentioned these to some extent. So cuBLAS is essentially NVIDIA's implementation of the BLAS on GPU, right? It can do things like dot products, scaling vectors, norms, blah, 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 blah. So matrix vector multiplications, level 2 BLAS, triangular matrices, full matrices, and so forth. Hermitian matrices. If you don't understand some of these concepts, no problem. There's always basic linear algebra texts. And of course, matrix. So the cuBLAS has its own dgem. And then there's a sparse library, which is, in my mind, well, it's their official product, but it isn't particularly cleanly written. But it is available. I'll talk a little bit about that in a minute. So to create matrices, you always have to construct a matrix. That's one of the limitations, right? Often in these problems, you don't want to explicitly construct the matrix. It does the sparse, it has sparse formats, which are handled through indexing arrays, and can perform the normal matrix, vector, and matrix, sparse matrix vector operations. There are fast Fourier transforms, and there's also random number generators. And I'll mention these again in a minute. Okay, that's the single GPU support we currently have from NVIDIA. So here's a quick example, a Saxby operation. I take it you all know what a Saxby operation is. Y is equal to AX plus Y. And if you want to use cuBLAS, you have to add a few things. So there's a corresponding cuBLAS Saxby operation. However, you need to explicitly declare and allocate the device vectors. You have to set those vectors to something, and you have to copy them explicitly from the CPU to the GPU, and then at the end, after it's all done, copy it back to the host, and correspondingly free them. A little bit of complexity, right? But the Saxby operation then runs on the GPU. So there's also a matrix multiply. This one here is a double complex version of the matrix multiply. And you will see this famous factor of 8, which I think Alistair mentioned. This is really this is a compute-intensive problem, so you really can exploit the floating point arithmetic unit of the GPU, and you're running at about 400 gigaflops versus a little bit over 50 on the CPU using Mchael. Remember, this comparison is socket to socket, so not necessarily a fair comparison. You could consider you might want to make a node-to-node comparison where you'd have 2 sockets of CPU versus essentially 1 GPU. But in any case, so the point being, you do get almost this factor of 8, which Alistair talked about, comes from the peak performance of the CPU versus the peak performance of the GPU. Okay. QSparse, like I said, this is only an introduction. I won't go into any detail of the libraries. QSparse is something it is a product from Nvidia. I sometimes have the impression it was written on the plane from one conference to another. It supports sparse operations. They're based on indexing arrays, sparse data formats, sparse matrix formats, and which are ultimately based on indirect addressing, right? And there are a whole bunch of sparse formats. The most famous one is compressed sparse row format. That generally doesn't perform best. There are much more complicated formats which do. For example, this hybrid format, which is an LPAC format combined with a coordinate triplet format, index value, which performs much better. And of course, you can convert between all these formats. That's already a lot of the library to make conversions. And then it performs sparse matrix vector and matrix products, and has super duper simplistic preconditioners, which are for real problems absolutely useless. Okay, so here's just a simple example. This is an Mchael sparse CSR, compressed sparse row, matrix vector multiplication with X. The resulting result is Y, and then a whole bunch of vectors which describe the matrix. And this is one of the, well, anyway, that's the Mchael version. And it was modeled, the QSparse was modeled on that. So again, you have descriptors and values and indices. I frankly don't find that a very clean representation of a sparse matrix where you'd like really one object to describe the matrix. My personal opinion. So modeled on this Mchael sparse support. And performance. This is a relatively old GPU, right? And you have 4 different representations: single precision, double precision, complex, single precision, complex double, and for a bunch of different matrices, sparse matrices, right? And then this is just the matrix vector performance in gigaflops. And what you'll notice immediately is you no longer have 400, well, on this GPU you wouldn't have that high anyway, but you're talking tens of gigaflops, right? Very modest performance. And that comes from the fact that now the problem is no longer compute intensive, it's memory bandwidth intensive, right? So you can essentially forget about gigaflops and have to be happy that you're getting a fairly high percentage of memory bandwidth. And for some of these matrices, the performance is frankly really bad. Around 1 gigaflop. Okay, there's QuaFFT, which is essentially modeled on FFTW. So you have FFTW, as you know and love, where you make a plan, you define the plan, and then you execute the plan for a particular fast Fourier transform. And correspondingly, you have a plan, create a plan, and execute the plan in QuaFFT. totally analogous to FFTW. Again, single node. Performance this is more compute intensive, right? This is somewhere between memory bandwidth limited and total and BLAS 3 sorts of operations. And on a fairly new GPU, I don't know what this is. I assume these are new results, and this will be a Kepler. You get a fairly high gigaflop rate. This is the log. You probably can't read this. This is a log, the log base 2 of the size. So to get this really good performance, you're already trying to do a 1D FFT of 10 to the 14th, 2 to the 14th, which is relatively large, right? So you have to put these good results in perspective. There's QRAND. I won't talk much about this, but you know, it implements a lot of state-of-the-art methods for uniform, normally distributed, log normal, and so forth. And this is what you would expect to have on GPUs. There were two ways to call it from the CPU, right? To get a big vector of random numbers. Or you can actually invoke it inside the kernel, which is very significant, right? You'll have kernels where you need random numbers, and you can grab them right from inside the kernel. Okay, so that finishes the Nvidia libraries, CUDA, libraries. I just make the comment, if you can use them, I mean, they're there on Daint. They are pretty solid. The Sparse library, I think there are other possibilities which are better. But otherwise, these would be the things to use if you're doing FFTs, random numbers, or just BLAS operations. Save things which have been optimized specifically by Cray and libsci. Okay, so now we get to Magma. Magma, you should think of essentially as LAPACK on GPUs. It's by the same people who did LAPACK. In other words, led by the University of Tennessee, Knoxville, Jack Dongara, and company. Essentially, the main version is written in CUDA, but there's also, there's also some limited availability for Xeon Phi and OpenCL. None of you will be using Xeon Phi because you probably don't have access to Xeon Phi. Is that right? Does anyone use OpenCL? Okay. Good. Not in this community, unfortunately. And then there's been talk of a distributed memory version, which would be essentially the equivalent to Scalapack. And they've been talking about this for years, and still nothing is available. So nothing concrete is available, but maybe I'll say a few more words about that. Okay, so what sort of operations does LAPACK cover, essentially? Well, it does things like simple factorizations of symmetric matrices, QR factorization, perform a least squares minimization, for example. LU is factorization, just a way to factorize a non-symmetric matrix, combine this with forward and backward substitution, and then you can actually solve non-symmetric systems. Eigenvalue decomposition. If you don't know this stuff, go back to your basic linear algebra text, but this is a very common operation needed. Generalized eigenproblem, maybe I'll say a couple words about that, and something called the singular value decomposition, which is very important, well, in many fields, signal processing, for example. Okay, so what's available? It's actually not looking bad. So Magma has support essentially for these. This is currently under development, so it probably should be yellow. Singular value decomposition, in my mind, is something which is under development, or there's a CPU version in Magma, but that isn't really what you want. You want the GPU version in Magma. Okay, so this is directly from, I think, last year's Supercomputing conference. Magma 1.3. There's a CUDA implementation, a OpenCL, and a Xeon Phi implementation. As you see, the CUDA implementation is the one which has the main functionality. Yeah? And just a little bit to performance. So this is the Mchael performance of the LU decomposition, solving these large, dense, non-symmetric system of linear equations. Matrices are very large indeed, so up to 26,000 squared, right? The Mchael version maxes out very quickly because of cache issues, and then you can run it on 1 or 2 CPUs, but caution, this is still not distributed memory. This is a node with 2 GPUs, right? This is good work. It's not going, since it's not distributed yet, there's still more steps which need to be taken by the developers to support your problems. Let's see. Oh, more on performance. These are some quite old results. This is a quad-core versus a very old GPU, Nvidia GPU. And what you notice here is this side, the left-hand side, is a QR decomposition, think least squares minimization. On right, LU decomposition, solve large non-symmetric systems. And what you see of interest here, well, the overall performance of single precision is not nearly as high before, where I was talking about 400 gigaflops in double precision, right? It's a much older GPU. And there's a huge jump between double precision and single precision, and that's because of the way old GPUs handled double precision, right? But the good news here is Mchael and LAPAC were down here. Mchael performing maybe twice as well as LAPAC, but still a factor of 3 or 4. The GPU is maybe a factor of 3 or 4 better, say 3 better than the CPU version. Okay, this is work which or the ETH, I should say, better said, is involved in. This is the implementation of the first stage of a generalized eigenvalue solver, which is to tridiagonalize a large symmetric matrix. Symmetric square matrix, obviously. And in this first stage, well, you can do it in different ways. First, Mchael. Cache issues, right? The performance actually stagnates with bigger and bigger matrix size because it's having fewer and fewer cache hits. That's a phenomenon you don't really see on the GPU, where things just keep improving. These are, for different numbers of GPUs, again, single node, right? Multiple GPUs, but single node. So maybe a factor of 3 again, CPU versus the GPU for one GPU. That's nice, but that's not really satisfying. So it's not necessarily important to understand how this operation is done, but basically the original implementation was essentially annihilating one column and setting it to 0, right? You can do that in another way. You can do that in blockwise, so annihilating part of it and setting it to 0, resulting in some sort of a band matrix, and then in a second stage, reducing that band to tridiagonal form. How that's done is not important, but the performance becomes remarkably better, right? Now you're getting a factor of 6. This is an algorithmic change, of course. Now you're getting maybe a factor of 5 over the original GPU version, and maybe a factor of 8 over the Mchael version. why does that happen? It's because you make a much better use of Blah's 3 operations, think dgem, and that's computationally intensive, right? So you're getting back into that computational intensive realm where the GPU is really, really good, okay? So this is work which is going on between University of Tennessee and also Raphael Solke at the ETH in Zurich. And hopefully will be integrated at some point into LibSci. Right? Yeah. Okay, so Magma, subset of LAPAC for hybrid multi-core platforms, also limited support for Xeon Phi. I think it's a very high quality library. It's proven its performance, no question. There's a clear need to replace Scalapack with something like D-distributed Magma. Unfortunately, there are delays, possibly because of funding limitations in the United States. I don't really know. But definitely a solid library which you can bet on in the future. Okay, so now we get into more the realm of sparse problems and some non-numerical or semi-numerical problems. There's a library called Thrust available, and the idea behind it is try to extend the C++ standard template library for GPUs in a sensible way. So to try to mirror STL on the GPU and giving easy access essentially to vectors on both the CPU and the GPU. It defines some very straightforward operators and to initialize vectors, exchange the existing values in vectors, copy one vector to another, transform vectors with some sort of given operator. I'll give you some examples in a minute. Perform reductions. In other words, take a one-dimensional array and perform some operation to get a scalar value. Again, I'll give you some examples. Sorting, and then there's some other operations. It's a relatively simple, compact, well-defined library. So here's some typical operations. You can define a vector on the host. Simple, right? It's templated. Templated means you say, oh, I want a host vector, and using that template, you instantiate it with for integers or doubles or floats. This is all CUDA C, by the way, CUDA C++. You can define device vectors based on the host vector. You can just define a device vector and initialize it to a certain value, for example, 1. You can define a sequence, 0, 1, 2, 3, et cetera. You can fill a vector. I assume you know what iterators are. Basically, these are iterators, the start of the vector to the end of the vector with the value 2. Fill D with the value 2 from beginning to end. You can perform transformations on vectors with, again, simple predefined operators. For example, negate the vector in D and set Z equal to the negated vector D. Yes. You can replace values. Every 2 should be changed into -2. You can perform reductions. For example, simple global sum of the vector D, right? You can sort arrays, very simple. Again, these are iterators, right? So from H to the 5 elements of H, if you like. So, simple manipulations. So this is a little tiny assignment here. You have to define, you have to use all these include files. It's a template library, right? It's all done at compile time. It's not, it's not a called library, if you like. Okay, so what do we do in this example? We define a device vector. with all ones. We initialize a host vector with the first 5 elements of D, right? From begin to begin plus 5 iterators, right? Fill the first 7 elements with 9, and then copy H back to D. So the question is, what is printed out at the end? Take a couple of minutes and think about it. Then I'll think about it because I don't know the answer right now, and we'll see if the answers are the same. Take 2 minutes. That's what I think I get. Does anyone get something else? Why do I think that? D initially has all ones, right? I might be wrong. I've just done that out of my head. So H is a vector with 5 elements, right? 5. Right, copy from D, right? So first 5 are ones. This D we fill in with 9s. So the 1s are overwritten until the 7th element. So it's 9, 9, 9, 9, 9, 9, 9. So at this point it's 9, 9, 9, 9. And then I should copy back H into D. H is 5 elements, these 5 elements, which are still 1, yep. And then it leaves this. That's what I get. Okay. Super simple operations. I mean, straightforward, it makes sense. You can, if you go online, you can be working with thrust in a few minutes. It's really quite simple. Okay. So there is an exercise. What time is it? That time can't be correct. It says it's 12:25, time for lunch. Okay. If you like, we'll do a compromise. Instead of doing this exercise, I'll do the exercise, and you can do it with me, and we'll see if we can do it in 5 minutes. How about that? Okay? So, now, okay. So there's this web page, Phomix GPU libraries. This course we did last fall. And now it's completely resized all the windows. So let me try this. Okay. And there are a whole bunch of exercises. So not only to thrust, but to several other libraries, which I'll try to talk about. There is a thrust example. Okay. And it's really very simple. Basically, it's to define an array, and then use the predefined sort, thrust sort to sort the array. Totally simple stuff. Here's the code. It's 47 lines long. Okay, And the idea would be, okay, this does the sorting on the host. The idea would be to get a GPU version which sorts on the GPU, or maybe do one sort on the CPU and then the same sort on the GPU and compare. So let's just try to copy that over here. Oh. This one. There's our program. Control D. Okay. And then there's some pretty simple instructions. Right? You just need to compile this with NVCC, right? So let's try to compile that with NVCC. In fact, here's even the line. Now we're not on 30, of course, but we're on Daint, so we can try to edit that. And let's see what happens. And it should fail. Why does it fail? NVCC, the Nvidia CUDA C compiler, isn't available. Well, you know how to fix that now. Module load Cray PE cell Nvidia 5. Okay. Now we should be able to compile. Okay? Well, obviously we can't run until we get an allocation on a compute node. So let's try that. And it's not like on Tuesday. Pending. But no one from the course is working. I'm not in the reservation though. I would have to have a course account. Okay, hold on. Here, there. Thank you. Now we're in business. We're in business. Okay. Okay. So we've compiled that, and now we just want to run on one core of the CPU, which isn't, well, it won't be a fair comparison with the GPU, obviously. But let's execute that. One core of the CPU now. And, probably I need a size of the vector like 100. I don't know what the default is. Okay, so we've sorted 100 values. It takes not a very long time. If you know a little bit about sorting, that should go as n log n. So if you do 1,000, essentially something like 10 times as long. $10,000. Okay, again, roughly 10 times as long, and so forth. Let's try 100,000, and we'll see. Okay, so let's quickly implement the GPU version. So let's copy. Host device. Okay. Let's go right at it. And edit with Emacs. Okay. And you have some initialization stuff. You create an event, not important. This is just for the timing, essentially. And the sorting occurs from this record event start to the record event end. And this is the section we want to duplicate, right? So let's just duplicate this. And then we could actually just comment this out. No one cares about what the values are. Okay, so now we want to do a host version of the same, a device version of the same thing. So let's not call it HVEC, but DVEC. And then the device sort took this long. Okay, so essentially we're done. I'm sorry? Yeah, thank you. Thank you very much. Any other HVECs? HVEC. That I commented out, that I commented out. Okay, well, now we have to define the vector. Okay, well, how is this one defined? That's just an n vector defined on the host. Now we need the same, essentially the same vector on the device. So let's do that here. Now you can define vectors, device, oh, excuse me. Where are we? There we go. Okay, instead of a host vector, we know a device vector. And now we can just define it through the host vector like this. Good. And then we've forgotten one thing, namely this is a template library. This is a template library. We have to include the template. And we should be done. If I haven't forgotten anything. It's always dangerous to do examples like this. Let's try to compile. Okay, I guess I don't have that line, so let's just go back here. Oop. Good. Host device Daint. I lost the environment. Why? But you shouldn't. You shouldn't lose the environment with a cell. Did I? Okay. 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 That's fine. Okay, let's try this. Okay, and now let's run it. AP run. Let's try 100. Well, 100 isn't really going to give much work to the GPU. And so the GPU is actually takes 5 times as long as one core of the CPU. But of course, this is a very, very short vector. What is going on here? Why don't you have history? There it is. Okay. That quickly the GPU starts to overtake the CPU core. And then you would expect a relatively large increase in performance over one core as you increase the size of the vector. So this is 100,000, and this should be a factor, well, we should be seeing factors of 20 or 30 faster. Well, factor of 70 faster. What we haven't taken into account, of course, is the copy from the host to the device, and presumably afterwards you'd want to copy it back to the host. That's something you can extend the example with. So very simple example to illustrate, yeah, this stuff does work, the device does do it a lot faster, and it's fairly easy to use if you're confident of using template libraries. Okay? Questions to that example? Anyone want to see the code again? The copies in this example are done in a synchronous way. You should be able to avoid that, to do it asynchronously. Let me get back to you on how that would be done. But this is definitely a synchronous copy. Okay, so this is the solution, exactly what we did. This time to sort the vector, device vector. Okay? Simple example. Okay, so Thrust, incidentally, was developed. It's a public domain library, but it was developed by Nvidia. It's based on CUDA, so that you're bound to, well, this isn't strictly speaking true. Now, there are implementations which are not bound to Nvidia. It is an open library. It was an open source project driven by Nvidia. But in a certain sense, it's still an official product because it's bundled into SDK releases. The idea of Nvidia is that they would start this effort and then it would somehow be taken over by the community in a demand-driven way. In the reality, it's not the case. I mean, if Nvidia weren't to invest resources in this, it would probably not survive. So let me move on to sparse linear algebra, right? So linear algebra, you've seen this probably hundreds of times. A matrix times a vector is equal to a right-hand side. We're generally interested, at least when you're talking about partial differential equations, A is a sparse matrix. And here are some examples of sparse matrices. There's actually a great site where you can go shopping for sparse matrices, sparse and dense matrices, called Matrix Market. What a sparse matrix is not really well defined, but say it's at least 90% zeros. Some people would say 99% zeros. And of course, the sizes are much larger than what can be done, for example, in Magma for dense matrices. So 10 to the 7th. This is actually an old slide. It'll now be 10 to the 8th, 10 to the 9th numbers of non-zeros. Okay, so to solve the system, there are essentially two different techniques. There are iterative solvers, which start with some initial guess and then progressively try to get a better approximation for the result. In other words, they try to minimize the residual ax minus b. And then there are direct methods, which are not unlike the LU decomposition, right? Which try to factorize the matrix. And that's very good if you have multiple right-hand sides, because you do this factorization step, right, of the sparse matrix, and then you can use that factorization again and again and again for multiple right-hand sides. These tend to be more robust, these direct solvers. These might not actually converge to a real solution. And just a little bit of historical background, because Stiefel actually came from Zurich, or was at the University of Zurich, and he proposed the conjugate gradient method, which you've heard of in some form. This is two ways to approach the solution. One is by following the gradient, right? This method of steepest descent. And this isn't a good method because it tends to bounce back and forth. if you use the conjugate, which is, well, what the conjugate is, it's essentially A transpose A times X, but that doesn't matter. Sorry about that. Turn that off. Okay. Essentially, you can get much faster convergence to the answer. And that led to a revolution in these, what are known as Krylov subspace methods, also for non-symmetric matrices. The original conjugate gradient is for symmetric matrices. What's interesting here is you never explicitly use the matrix. You use a matrix vector product, right? A times P here, and 1 here. And you don't really need the matrix. All you need is the value of this operator, matrix times a vector. Well, people found that method very interesting in the 1950s and then quickly lost interest. Why did they lose interest? Well, it theoretically converges 2 to the n steps, where n is the size of the matrix. If it's a large matrix, that's like 10 to the 6, 10 to the 7th. That's a lot of steps. And the convergence rate is related to the ratio of the smallest to the largest eigenvalue. So people lost interest in these methods until someone suggested, well, something called preconditioners. If by chance you can find a good approximation for A where the inverse M is relatively easy to compute also, right? Then you can reformulate this problem in this way. It will give the same answer. I'm just multiplying on the left-hand side by the inverse. We said the inverse is somehow easy to calculate, while M is still a good approximation for A. And this will change, this can change, or actually will change, this ratio of smallest to largest eigenvalue, and therefore speed up the convergence. Well, there are a lot of ways. There's huge amounts of research has gone into preconditioners. There are lots of possibilities. One is to do not an LU decomposition, but fill in some of the values of the LU decomposition, but not all of them, to keep it sparse. There are lots of other ways. Multi-grid preconditioners, a very effective way. And that gave resurgent interest into these Krylov subspace methods. So there's a library also from Nvidia, open source initiative called Cusp, which tries to implement some of these iterative solvers, along with some fairly simplistic preconditioners. It's built on top of thrust, and you'll see similarities to the previous example. Now you have an object which is a hybrid matrix, right? There are, again, different types of sparse matrices, hybrid matrices, CSR matrices, and so forth. There's facilities to read in from this matrix store, this matrix market, which has its own matrix format. You define a right-hand side and some sort of initial guess for x, which can be 0, and you solve it. Simple as that, right? Again, single GPU, right? Okay, we've actually invested a little bit of time through summer internships for students into this library, trying to implement slightly better preconditioners into it. These preconditioners require a QR factorization, which I talked about before, not a sparse QR now, but a dense QR, which is available, for example, in Magma. And so we've extended this Cusp library with some fairly effective preconditioners. This is called a sparse approximative inverse preconditioner, now available in this library. Okay, so Cusp is an attempt to sort of build on thrust with template metaprogramming to address with some extra sparse with some sparse matrix formats to support linear solves, iterative solvers on GPUs. Still single node, right? I made a comment here, the multi-node version, I'll get into this later, the multi-node version should be at a higher level of abstraction, but I'll get into that later. Has only backends, well, like thrust. This is the same backends as thrust, which is essentially NVIDIA GPUs. And the big problem with this is NVIDIA started this effort, hoped it would be taken over by the community, scientific community, and that didn't happen. So basically, they no longer support it. You can expect it. This future isn't uncertain. It's certain that it will die out. But it is available on GitHub if you want to play around with it. I added this slide this morning. So NVIDIA isn't supporting Cusp, but they've gone in a slightly different direction. They do want to offer some sort of linear solvers and preconditioners. There's a page where you can look at this AMGX library. This is now a proprietary library with a commercial license. We do not have it on Piz Daint. However, if there were sufficient interest, we would probably try to acquire that. Again, single node, and the same sort of methods you saw before. It's not a template library, it's a callable library. Same sort of Krylov method, so with the addition of algebraic multigrid. If you don't know this technique, it's a very effective way. Multigrid, you usually have to know something about the structure of the underlying grid. Algebraic multigrid is a way to avoid that and try to extract the structure out of the matrix. Still requires you to construct the matrix. It's a fundamental deficiency in the library. Has open MP support, and ostensibly, well, it's not ostensibly, it does have MPI support too. It should do multi-node. However, that's not really effectively implemented because it effectively means you're performing a different algorithm. You're not performing the same solve. So this, the multi-node version can take much longer to converge or not converge at all. And in my mind, that isn't an effective tool if the multi-node version gives you different results than the single-node version. Okay, I just mentioned that because that is what NVIDIA has tried to push now. We don't have it on Piz Daint, and it would be interesting if there was any interest in it. Okay. However, there's an open source initiative called Vienna CL for sparse linear algebra. And what's neat about this is the CL implies open CL, which none of you use, as we've ascertained. However, they quickly realized that that wouldn't be a very good product, and so they've defined multiple backends for OpenMP, which could be run on mic or on the CPU, OpenCL, which could be also, in fact, be run on a GPU to a certain extent. There's also a CUDA backend. Same sort of idea. Well, I'll get into the structure in a minute. As iterative solvers, multiple sparse formats, and it's built, well, it's extracted ideas from the Boost library. Boost, if you're C++ programmers, you certainly know Boost. I'll talk about that in a second. It's, again, an open source header-only library, templated library. So in Boost, there's something called ublas to solve, this, for the solution of, for simple BLAS operations. Here for dense matrices, right? So this is a very simple way to solve a linear system within ublas. You can do things like scale vectors, perform an inner product on two vectors, an outer product. So one is X transpose Y, the other is X, Y transpose, the outer product. This forms a matrix, this forms a scalar. You can do solves, again, dense linear algebra here, right? And just write out norms. Okay, so Vienna CL takes the same design as Boost UBLAS, and you can similarly define a dense system using still a dense system, just like you could in Boost, and do exactly the same sort of operations, but from within Vienna CL now. And there's a solve, same sort of solve, essentially an extension or the same functionality as Boost. No. It has their own backend. Okay. Then they've added a memory model, which essentially abstracts memory to whatever is available. You have those three backends. Well, obviously, they need some sort of common interface to different backends. You can create memory abstractly. You can copy memory abstractly. You can write memory and read memory all abstractly. And the memory itself, well, that depends on which backend you're using, right? So it interoperates with Boost. Well, actually, not only Boost, but with other tools which are often used. And you can start mixing and matching. For example, you can copy a standard, an STL vector, for example, a standard vector, for example, to a Vienna CL vector, same way as in thrust. You can copy a Boost vector to a Vienna CL vector, and et cetera, et cetera. Now, what makes Vienna CL different from Boost UBLAS is Boost UBLAS has no support for sparse matrices, but Vienna CL does. So now you can define a compressed matrix, right? So this is a 1,000 by 1,000 matrix, but it's not in a dense format, right? So it's not a million elements. It's presumably in this compressed sparse row format. Then you can perform solves using this sparse matrix. There's no equivalent in UBLAS. However, because they're interoperable, you can still get a UBLAS, a Boost vector out of the calculation, right? So you perform the calculation in Vienna CL, right? But using with a compressed vector, a compressed matrix in Vienna CL, but your vector, your result, is still a Boost vector. Or your right-hand side, in this case, is a Boost vector. So the whole idea of Vienna CL is therefore to interoperate with existing libraries, which is a very powerful concept. So this is just briefly, this sort of expression causes a lot of trouble when it's expanded as in template metaprogramming. Why? Because it implies that there are lots of temporary vectors, right? If you do this, well, you calculate this, that goes into a temporary, you calculate this, that is in a temporary, you add these two, that's another temporary vector, then you have that plus the temporary vector. It could be very inefficient. Well, there's a mechanism called expression templates, which will minimize the effect of these temporaries and hopefully do it in the most efficient way. Therefore, you can expect Vienna CL, even though it's a template library, to perform fairly well. It's also a concept used in other libraries. So there is an exercise. If you're interested, please go to the course website. Again, very simple exercise to take a Boost solve and then extend it to a Vienna CL solve. Okay, so Vienna CL is nice because it's a logical extension from Boost, which is a very, very popular a library. There are backends, multiple backends for OpenCL, CUDA, and OpenMP. Therefore, it supports Xeon Phi, normal CPUs, and Nvidia GPUs. It is under active development. It seems like it will have a longer-term future. These people are incidentally very well networked with other library teams. It has more than adequate selection of solvers and sort of a minimal number of preconditioners, but non-trivial preconditioners. Some are fairly effective. Performance results are evolving. They need to do a little bit better in terms of the code they generate. It interoperates with a lot of really cool libraries, not only Boost, but something called Eigen. The PETSI group, which I'll talk about in a minute, is very closely connected with the Vienna CL group, and there are others. And I'd say this is promising. I wouldn't bet all my money on this, but it's a library to keep in the back of your mind, just like these libraries, Boost, Eigen, PETSI. Okay. There's something called Parolution, which is much like Vienna CL from the functionality. In other words, it has sparse iterative solvers and preconditioners. It targets CPUs and accelerators. OpenMP, CUDA, that tries to make those opaque to the user, and it's to generate portable code. There's a website. The structure is slightly different. The idea is to have some sort of dynamic switch. If it notices an accelerator's available, then it tries to do things on the accelerator. If no accelerator is available, then it snaps back and just runs on the host, which is a fairly effective model, right? Everything is decided at runtime and not at compile time. They are working on new backends. This is actually more concrete now. There is an Intel Xeon Phi backend, possibility to have other backends, depending on what technology arises. Everything local. By local, it's meant single node now. So a matrix on a single node, local to that node. Very simple example of applying a matrix, doing a matrix vector multiply on the host. There's nothing about accelerators yet. Okay, so slightly with a few minor additions, right? We move A to the accelerator, move X to the accelerator, move Y to the accelerator, because I guess Y is being incremented. And this should all now run on the accelerator if the accelerator is available. If it's not available, these will be essentially ignored, and it will directly perform the matrix vector multiply on the host. Okay, so they've put in a lot of work into preconditioners. Some of these are really non-trivial, very effective preconditioners. Chebyshev, incomplete LU, they're quite powerful preconditioners. Also a number of solvers which aren't available in other libraries, multi-grid solver, for example. Quick example, to solve a system now. Again, things are defined fairly opaquely. You don't know where these are actually being stored. It depends dynamically on what it finds. You move things to the accelerator, right? The matrix, obviously, the right-hand side, X, and then you perform the solve. If the accelerator is available, it will actually perform it on the accelerator. If it's not, this will be essentially ignored. It will perform it on the host. So the real thing which sets it apart is that it's makes runtime decisions about the backends. There are multiple backends. It is being actively developed by the Parolution team. And what I particularly admire is they've put in a lot of work into state-of-the-art solvers and, well, a minimal spectrum of preconditioners, but quite effective preconditioners. Again, performance is evolving, and there's some plans for multi-node extensions, right? Okay, so that was essentially linear algebra. And last, let's see, 20-some minutes, I'll talk about going beyond linear algebra to solve more extensive problems, right? So, distributed memory, right? There are some plans for multi-node, but most of these libraries, or actually really none of them, implement it. There are some multi-node developments going on. I think I mentioned at the very beginning, Magma. There's some plans for distributed Magma, and some things have been implemented. There's something called PETC, which has concrete plans, is a distributed memory library, and has plans for GPU, or actually current development. And there's something called Trilinos, which I'll talk about too, which has concrete development efforts. I have to say, though, the current multi-node GPU support is provisional at best. A lot of good development has to go on. We don't even have these two, there are development versions of these two libraries with GPU support. However, they're not installed on Piz Daint currently. Okay, so PETC. Who has ever heard of PETC? Good, so that's a few, at least a couple. I would really have to give you a little introduction to PETC. Well, what is PETC? It's essentially a library to support partial differential equations, right? And there were many efforts in the 90s to put support for PDEs into libraries, and this is essentially the library which won out. It's free, it runs on different platforms, from your laptop to Cray XC30. It's installed on Piz Daint, not with GPU support, unfortunately. There's active maintenance, there's a group of 10 people working on PETC. Basic idea is to let the scientist think only of the mathematics of the problem, and then give support using through mathematical high-level abstractions for things like sparse matrices, nonlinear equations, algorithmic objects like solvers. The whole library is written in C, incidentally, not C++. There are a number of different solvers. A lot of consideration has gone on into the distributed memory aspect about how data is distributed. Okay, this is the structure, and it has many, many levels, all the way from MPI down here. Obviously, use BLAS at a low level. Also, Thrust, Cusp, and Vienna CL are supported in the development version of PETC. It has integrated profiling, which is really cool. Then it has these abstractions for matrices, vectors, and indices, and other things. Has a whole bunch of linear solvers, state of the art, right? Nonlinear solvers. There's a visualization interface. At the very top, you have integrators of ODEs. And the idea is that everything in yellow is PETC, basically. So what does the user have to do? Well, user has to write a main routine. Has to somehow initialize the application, obviously. In the linear solvers are available in PETC. If you want to do a nonlinear solve, you have to provide an evaluation of the function, so some subroutine which evaluates your function, and possibly a Jacobian evaluation, so essentially the first derivative. And then any post-processing you need to do, obviously, you have to write yourself. So The goals, I think I mentioned, it's supposed to be portable. It should run anywhere from your laptop to the Cray XC30. It should be performant and scalable distributed memory parallelism for these PDE problems. I think I mentioned many of these things already. There have been additional classes added for GPU support. I'll get to those in a second. The parallel complexity, this is a key thing. They try to hide the complexity of the parallel objects, and I'll show you an example in a second. So there are these high-level objects, vectors, matrices. We'll get to an example. Okay, so everything is distributed memory. So processors can generate entries into vectors anywhere in the vector, not only into their local chunk, but anywhere, right? So at some point, the vector or matrix is assembled, and at that point, obviously, PETSI has to decide, oh, these data which were created here on this process have to go over here to this process. But that is all opaque to the user. So maybe we even get an example here. Oh, no, this is the communication. Yeah, no, here we are. So you create a vector, right? This is a collective operation. Every process has to do this. Some operations are not collective, for example, to get the local size of a vector. Most are collective, like calculating a norm of a vector. Oop. Sequence, they have to be called in the same order. Okay. State-of-the-art solvers, all the ones you've seen before and a lot more, and state-of-the-art preconditioners running in parallel. Okay. So, I'm sorry, I thought there was an example here of the communication. Oh, I didn't put that in. So, PETSI is being extended for GPUs to interface to several of the libraries I mentioned, Cusp, Vienna CL, for example. So the idea is every MPI process has access to a single GPU, right? And that's a very good abstraction for Piz Daint, where that's exactly the case, right? Multiple backends for these libraries I mentioned, QSparse, Vienna CL, Cusp. And this requires new implementations of these abstractions for matrices and vectors. So you have things like vector sequential Cusp, MPI in Cusp, so this would be distributed over multiple nodes. And similar for matrices, matrix distributed over multiple nodes, which is using this sparse row representation of the matrix, QSparse, etc., right? So lots of extensions of these abstractions for different backends, and then some sort of abstraction, some sort of flags, actually, which determine where the values are actually up to date, right? Whether they're unallocated, whether the GPU has the current value, the most current value, whether the CPU has the most current value, or whether they're both up to date. Then there's functionality to support movement from at a very low level, which you can use, but you can also use this PETSI support at a high level where you don't have to move data yourself. These are generally used internally in the solvers, so chances are you would not be working with these types of, at this level, right? Okay, so what's the status? It essentially works, or allegedly works. I tried to compile it myself, and I couldn't get it to compile currently. Ultimately, you use these additional abstractions for vectors and matrices, and that should invoke the corresponding backends, Cusp, QSparse, Vienna CL. The implementation should conceptually be transparent to the user. You can program at a very low level, for example, in CUDA, and access the objects directly. But the idea would be not to do that. Just use the very high-level ones, which use the backends. And this is actively discouraged. What's the status? I've tried myself. I couldn't get the GPU support to compile. It will get better. At a certain point, the PETSI team will release an official version with GPU support. My knowledge, that hasn't happened yet. Therefore, since there's no standard support in a standard release, it's not available in Piz Daint. As soon as it is, obviously, we will install that. Okay, so PETSI is, in my mind, pretty much the way to go. It is a high-quality library. It's been around now for 15 years or so. It's free. It's much better for new code than existing code. That's an aspect I didn't mention. Since you have these abstractions for matrices, vectors, and so forth, of course, you have to use those abstractions in your application. It has some design choices which were what might have been appropriate on the, at the time. It's not thread safe, unfortunately. And it's a monolithic library. One library tries to solve a really large spectrum of problems, although there are adapters or interfaces to other libraries. I've said this already, so the distributed memory GPU support is under development. You can play around with it in a development version. However, it's not available in their standard release. Okay, that brings me to the last library, which is called Trilinos. Trilinos actually isn't a library at all. It's what is known as a Perl necklace of different packages. So it's more of a framework, right? Some of these packages, the packages address different issues in physics, basically, physics and engineering. And some of them interoperate very well, and some of them interoperate very poorly or not at all. It is a big effort led by Sandia National Lab. And it does lots of things. I mean, basic linear algebra, like we've seen before. Preconditioners, as we talked about. Iterative solvers, we've talked about. Direct solvers, which we talked about very briefly. Nonlinear solvers and optimization problems. Eigensolvers. Mesh generation. Domain decomposition. Partitioning. And then some additional ones on top of that. In red are the ones with GPU support. So they do have a model for GPU support. I'll just say a little bit about that in the next few slides. And nearly everywhere you have higher level packages which make use of the lower level basic linear algebra, which includes the GPU support. Okay, so super briefly, how do they implement this? Well, they try to make, again, an abstraction for the low level by abstracting things like a reduction operator and a loop operator, right? For a reduction, think of a dot product, which obviously requires a reduce. And for a parallel loop, think of an AXP operation to add two vectors together. And then you need a way to fuse kernels, which are built up of these basic building blocks to build higher level operators. So template metaprogramming, I've mentioned that before, from Thrust. That's the way it's all implemented. And just as an example, these are these classes, these template classes for a parallel for a parallel reduce. Won't go into those in any detail. But for example, this is how an AXP would look using this parallel for abstraction, right? Then the basic kernel operation is very, very simple AXP operation. Similar for a dot product, basic abstraction, right? This parallel reduce, and ultimately the parallel reduce only returns a basic addition of the elements, right? So then you have these abstract kernels, and then you have some sort of backend which converts it to the right type of kernel, whether running in serial or with pthreads or with thrust or with CUDA, and of course this model could be extended. So this is a fairly sophisticated way to support higher level operations. Okay? Now, this is one of the libraries which has implemented this COCOS model, right, called Anasazi for eigenvalues, and this is something which our customers would, potentially use. The Lanczos algorithm, perhaps you've heard of. It's the equivalent for eigenvalues of the conjugate gradient algorithm is for linear solvers, and I won't go